Hi everybody, welcome back to the lecture Computer Animation, and this time about rendering. So here we will talk about building the rendering pipeline, which includes local lighting models. So we have a virtual light, which we need to include to see our object. Then we need shading methods, which is how the light is reflected from our virtual objects. And later we also need to take care of aliasing. We also will take a look at global illumination models and effects like shadows and motion blur. So first to the rendering pipeline. So we can see we have successive processing steps in the pipeline, and that also makes parallel processing possible. And depending on the details of the process, there may be differences in the structure. So the input data is our 3D objects and our 3D scene, which contains those objects. And that means we have 3D geometries and an arrangement of objects in our scene. And we need lighting information, type and position of the light sources. And we need information about our virtual material. And for that we need a lighting model. And we also need to have camera information for our virtual camera, the position, focal length, and so on. And the final output data would be the rasterized 2D image. So this is what's then finally displayed on our display. So here you can see it. We have the model. So here we have a transform to transform the local 3D model to the world coordinates. Then we have lighting, our virtual light. Then we need to have in this camera the view transformation, clipping, coloring, and rasterization. So what is this? So first the transformations. This is the transformation of objects from local coordinate systems within our model into world coordinate systems. Which then also defines the relationship between different objects. Where in the world is our object? And this transformation from the world coordinate system into the coordinate system of the virtual camera is first 3D using the view matrix, and then we have a projection from the camera coordinate system into the image plane, where we basically omit this one dimension. And this can be done with perspective projection or orthogonal projection, as we saw in the beginning. And then we need to convert it to pixel coordinates, the viewport transformation. So clipping and culling is part of getting rid of information which we don't see. So here the goal is reduction of geometry to speed up the rendering process and the removal of non-visible parts of the model. Clipping here is the cropping of the 3D model to the area that can be seen by the camera, called the view frustum. We can use, for instance, backface culling, which removes all polygons whose surface normals point away from the camera because they reflect the light in the other direction. So they are hidden. Then we have occlusion culling, which remove all the polygons that are hidden by other objects. So not on the back, but on the front, but hidden by another object. The input here is complete geometric scene description, and then the output is visible geometries. So here you can see it. Here we have our virtual camera. And then we also define a far plane and a near plane. And also only objects within these two planes are visible in our virtual camera. So if the object is too close or too far, it's also ignored. And then we only have objects within this 3D part pyramid. So here you can see it. Here the green ones are fully displayed and the yellow ones are partly displayed and the red ones are ignored. That's from this website here. Yeah, so then we have the clipping. Here we have the case differentiation. The polygon lies completely within the view frustum, the green objects. Then the polygon is output unprocessed, so it's fully viewed. Then in the case the polygon lies completely outside the view frustum, then the polygon is discarded because it's not visible. Then the polygon lies partly inside and partly outside the yellow objects. Then we need a special treatment. We need to divide the polygon into visible and non-visible parts. So then we need to check if polygons intersect with bounding planes of the view frustum. Yeah, so then we have the occlusal culling, determine the depth arrangement of the polygons and occlusion. So for the backface culling, we have polygons whose surface normals do not point towards the camera, and they are usually located on the back of complex surfaces, so they are not visible. And that means about 50% of all polygons can be eliminated by the backface culling because they are pointing away from the camera. So it's actually quite easy, the calculation. You determine the surface normals, which we call n. Then we determine the vector from the polygon, the vertices, to the camera, the virtual camera. And then we compute the scalar product of those two vectors. And if the scalar product is less than 0, less or equal 0, then the polygon is not visible. Right? So here you can see it. We have this polygon, this triangle with those 3 points, those 3 vertices. And then we can compute the normal vector as a cross product of the edges. So we have P1 minus P0. So here's the first vector from P1 to P0. The second one goes from P0 from P0 to P2. So here goes in this direction, and then we compute the cross product, and that gives us a vector vertically on this triangle. And if this vector n is perpendicular on the it's parallel on the vector of between E, the position of the camera, and in this case the vertex P0, right? Then it's visible. Otherwise, if this is less than 0, that means the normal points in the other direction, then we can discard it. So if this is positive, that means the normal points towards the camera. If it's negative, that means the normal points away from the camera. Yeah, so here's an example. Here the geometry included in the view frustum but hidden by other objects does not need to be rendered. So here you can see top view, here's the occluder and then the objects behind it from the camera. So those objects cannot be seen. This can be seen, the blue one, and the violet one can be seen a little bit, as you can see here. So one of the ways we can do the occlusion culling is Painter's algorithm. So basically we sort the polygons in Z direction, meaning perpendicular away from the camera, and we draw polygons in order from back to front, right, as you can see here. So here we have a complex object or an arrangement of objects, and we start with the one which is furthest behind, and then we draw the ones which are on top of it. And so what's left is the occlusion then. So if we draw it on top, then we have automatically the occlusion. The problems here is that polygons cannot always be sorted uniquely. Say if one is not really parallel but more or less diagonal. We have problems with overlapping space, and it's inefficient. Areas lying on top of each other are drawn multiple times. So here we have a way of occlusion culling by clipping to a shadow volume. So from the camera direction, the volume in which polygons are hidden behind an object is determined. So this is good if we have, for instance, walls. Like here we have our virtual camera, and we can see this room completely, which is green, and then we can peer through the doors that you can see here, and that gives us those areas which are visible, and everything red is invisible. So we can basically discard all the objects which are in those red spaces. So invisible polygons can be removed by clipping. But this leads to higher computational complexity, but this is possibly compensated by reducing the polygon set. So if a lot of objects are in these red areas, that gives us a lot of savings. So there are also numerous other implementations, and the goal is always to have as few arithmetic operations as possible. Yeah, so for the occlusion we need the Z buffer. So this denotes the Z-axis, which is away from the camera. So there's the axis which points away from the camera. And the starting point is that all values are set to a maximum. And then we have the rendering process steps. We have the interpolation of the Z values for each pixel of a polygon. Before pixels are rendered, we compare the Z value with the current Z buffer content. And the pixel is only rendered if the current value is smaller than the previous value, which means it's closer by. The new value is then written into the Z buffer, and then we repeat with further polygons. So basically this means we only draw polygons which so far are not hidden. Yeah, problem here is so-called Z-fights. This occurs with nearly coplanar polygons, which have a small distance to each other and partially overlap. And interpolation can lead to varying results. So overlapping areas can flicker, for instance. Solution: using a higher accuracy of the Z buffer, for instance by reducing the distance between front and back clipping planes, and increase the distance of the affected polygons. So here's an example. Here we have a bunch of different objects which partly occlude each other. And here you can see the Z buffer, which is basically giving the depth of each object. Right, so bright means nearby, and dark gray means further away. Yeah, and then we come to lighting. So this is our virtual light source. This determines the brightness and color for each vertex. We use physical properties of the surface for calculation. So basically this is a simulation of what really happens when we shine light on an object. For this we have local illumination models. This uses or computes only light that falls directly from the light source onto the object which is considered. And this is quick and easy for the calculation, but this also leads to a not very realistic representation, because usually we have reflections from the walls of our room and also from other objects. Right? Light is reflected from all objects, and so they illuminate each other. So this is taken into account by global illumination models. They also consider the interaction between illuminated surfaces. This leads to very realistic rendering, but also to a very high computational complexity, because there are many light rays. Yeah, so first to the local lighting models. We have different procedures which are in use. For instance, the Lambert lighting model, which we see in a moment, then the Fung lighting model, the Blink-Fung lighting model, and the Koch-Torrance Sparrow lighting model. And they differ in computational complexity and the physical correctness of the representation. So the simpler they are, the worse the result. So computational complexity. Okay, so here's probably the simplest, the lighting model according to Lambert. This simulates a Lambertian surface, which is an ideal diffuse reflection. So it's like paper, right? You shine a light on it and you get something diffusely reflected. And the strength of the reflection, you can see it, depends on the angle that the light exits. So we have incoming light here. So here's the angle from the normal. We have incoming light, and the blue rays are the reflected light rays. And we can see, depending on which direction they exit the surface, they have different strength. And you can quite easily compute it using the so-called Cosine Law, which is basically the proportional to the cosine of this angle, right? So, and this angle is only dependent on the normal of the surface and not on the light angle, right? So here this alpha is not even used in this formula. So it only depends on this angle from the normal. So basically it depends on the direction on which we view the surface. So if we view it directly from above, we have the strongest reflection, and if we view it from the side, we have less reflections, but then we have also a higher density, so that in total we get the same illumination effect. So for the viewer, it only depends on what angle this light actually shines onto it. So that means we have this angle here, alpha, which is then basically implicitly going on in this expression, Li times the normal vector n. So here we have this normal vector, and then we have this vector from the light. And when we compute this vector product, that is the same as taking the magnitude of L, the light intensity, times the magnitude of n, which would be 1, times the cosine of alpha. Right? So this is where we get the cosine of alpha. Yeah, so this ID is the strength of the incident light. So actually when you say L is a unit norm vector, then ID would carry the strength of the light. Yeah, and KD would be a coefficient for the reflection. So this is basically telling us how much light is reflected from the surface. For instance, if we have a dark paper, then there's less reflected. If we have a white paper, there's more reflected. Yeah, that's pretty much all we have here. So very simple. So the brightness is independent of the viewing angle. It only depends on the angle of the incidence of the light. And an example here is uncoated paper. All right. Yeah, so this is only good for non-specular reflections, and often we want to have surfaces which are somewhat shiny, which have some specular reflections. So then we need to refine it to add for a specular part, which we have here in the lighting model according to Fung. So it still is a highly simplified model for the representation of not purely diffusely reflected light. So here the first part is basically like what we just saw here, Lambert's reflection. But here we have this second part now, and also this first part. So here we can see, so the diffuse part is like Lambert. Then we have the specular part, the shiny part is the KS and ISI. And here we have a RI for the reflection vector. And we have this A, which has an ambient part. So it also has this ambient part, which means this is what we assume to come from other sources, like walls or other objects. So this is not precisely modeled, but just with this simple additional factors here, or additional coefficients. Yeah, and then we also have a gloss factor alpha, which describes the roughness or shininess of the surface. Here, this alpha. And the K are material constants, and the I are light source constants. Yeah, so here's the result. Lighting model according to Fung. So here's the final result on the left, and it consists of those three parts. Here's color and ambient. So this is the light coming from all directions. Here's the diffuse reflection. So this is Lambert, basically, the Lambert part. And here's the specularity. This is the shiny parts, the highlights, which basically model the reflections of a point-like light source. Yeah, so here's a alternative lighting model according to Blin. This is a simplification of the Fung model. You can see we have still those three parts. So it's actually quite similar. And the visual results are comparable with the Fung model. The results may be even more realistic. Yeah, so besides those simplifying models, we also have theoretical illumination models. So Fung and Blin are more empirical models, very simple, and they kind of work. But the alternative is theoretical models. They are physically correct with respect to the law of conservation of energy, Helmholtz reciprocity theorem, and the Fresnel equation. An example for it is Torrance and Cook. Disadvantage is high computational complexity. Right? We really need to simulate with high precision. So in between we have the Schlick illumination model, which is fast and approximately physically correct. So here you can see different results, and you can see they all more or less look okay, but have their fine differences. Yeah, and then we need a shading method for the interpolation between the brightness and color values of vertices. Remember, we have a surface, and the surface might be more or less coarsely covered by our polygons, and that means we need a useful interpolation to get good results. So this defines, together with the illumination model, the material properties of the surface. Common methods are flat shading, Gouraud shading, or Fung shading. So first, the simplest, the flat shading. So here on the right you can see a sphere, and the sphere is more or less coarsely represented by those polygons. And if, as physically correct, we give each polygon a constant brightness, then all of a sudden it becomes visible that the polygons on the sphere are rather big. So this might not be what we want. So this is a very fast process, well suited for shading flat surfaces, but this makes individual polygons visible because of the different gray shades that we get in this way. And that's unfavorable for the approximation of round surfaces as we have here. So we have this so-called mug band effect. This is the physiological contrast enhancement at the edges. So if we have two surfaces with different gray shades, then the eye can easily detect those different gray shades. Yeah, so that's why we look for an alternative, which is the Gouraud shading, or also called smooth shading. So here the polygons don't have the same brightness everywhere, but these brightnesses, the gray shades, are interpolated, so that we don't as easily see the polygons. So the polygons here are now less visible, but still looks kind of artificial. So for each point within the polygon, we have linear interpolation of the brightness and color values between the corresponding vertices and edges. We have one illumination calculation per vertex, which is fast. Right, so there should be a comma. And we have polygon edges which are not directly visible, so because they are smeared basically from the interpolation. But bending in the brightness gradient leads to the mug band effect at the polygon edges. So you can still see the polygon edges somewhat. So the corners are visible at the object edge. So here you can see the object corners. And we have also loss of highlights. Right, there is no specular reflection. Yeah, so that leads us to the Fung shading. here for each vertex, the interpolation of the normal vectors is done, right? So instead of just interpolating the brightness, we now interpolate the normal vectors and bend them, like we can see here in this picture here. So in the middle it's still normal, but then when we go to the edges, they are bent towards the next polygon, right? And remember, those normals were essential to compute the reflected light. So that means the reflected light is really computed as if it was coming from an object which was curved, like here in the red dashed line, right? So the reflected light really looks like coming from a round object. So this is a physically more correct way of interpolation. So that means for each point within a polygon, we have an interpolation of the normal vectors between the vertex normals. And afterwards, we determine the brightness and color value with the help of an illumination model. And that also means highlights are preserved. So here you can see the result. We have a nice highlight. The surface really looks round. Just when we look closely here at the object boundaries, we see that it's still consisting of just a few polygons. Right. So that leads us to the first Python example. So in OpenGL, we can activate the depth buffer, the Z buffer, with this command. Right, GL clear, then we have GL color buffer bit, and here GL depth buffer bit. So this gives us the Z buffer. Yeah, and then the shader is defined with this command. So we can choose either GL flat, the simplest, which is constant per polygon, or GL smooth, which is interpolated. So this is Gura shading, right? This in simple interpolation. So it's still not great, but better than the flat shading. Yeah, then we define the reflection properties of the surface and the color of the specular reflected light. So this should be reflected in RGB, red, green, and blue. So here you can see it. Here's the material values in floats as vector. Here we have specular reflection, and this is the RGB value here in floats, 1.0, 1.0, 1.0, 1.0. So this means white light. And here this defines how highly or how reflective the surface is. So here this is the shininess. Here I give it the value 10. Right. You can also read more about it here on this web page. Yeah, and then we have to define our light sources with positions. Right? We can define several light sources, so we need to number them. For example, the position of light number 0 in homogeneous coordinates, so here again we use homogeneous coordinates, is this. Again, here GL light and float values as a vector. Here for light number 0. Here we define the position as float vector. Here we can see it. So we have X, Y, and Z, and this is the W, so this is 1 in this case. Then we can define the radiation characteristic, which is defined with intensity and light color of the light source, for instance diffuse, which means light from one point in all directions, and with the light color and intensity as RGB in the argument. So here we have a light number 0 again. So here we start with the same function, GL light float vector for light 0. Here we define its diffuse, so light goes into all directions. And here's the light color. So here we have RGB, so this is mostly red and a little bit green and a little bit blue. Then we also can define an ambient light portion, which means light that comes from all room directions. So not from our light source, or not directly from our light source, but we assume it's reflected from all directions. And here we can define a different light color and intensity. So here you can see it. So this could happen, for instance, if the walls have a certain color, then they change the light color. You can see it again, RGB. So here the reflected light is reddish. So some red, but no green and no blue. Yeah. And finally, we have to switch on the lights. And we do that in OpenGL with GL enable. First, lighting in general, and then we can enable those two different lights. And we can also enable the depth test. So basically the Z buffer. Yeah, so here's the example. Solid cube light. So let's take a look at it. So copy. And let me go to my terminal window, gedit, paste. And now we can take a look at it. So here's this program. So again, as usual, we define our display, the display function. Here we have perspective mode, and here the position of our camera. And here we define the object which we have in our scene. So this is convenient because we have predefined objects like solid cube, solid sphere, and solid teapot. And here I select the solid cube of size 1.0 in the origin, and this is the object that we want to illuminate. Yeah, so first we want to use the cube. We can also then exchange it with those alternatives. So in the main part we define our window for our virtual camera output with this name here. This is the background color, dark gray. Here we have the shading model, GL flat. And here the color of the reflected light, specular reflected light is 1. Here we have the shininess, a lot of shininess here, 127. And here we have our lights. So here's light number 0. Here is the position in homogeneous coordinates, x, y, z. Here we define the diffuse light, so it shines in all directions with this light. So this is a somewhat reddish light here, and it also has an ambient component, which is also somewhat reddish and somewhat darker. Then we have light number 1. This is stronger and is red-green, and it also is diffuse. Yeah, this is position. Sorry. So X, Y. So this is the different positions, and this is the light that it emits. So it's kind of greenish light because green has the largest magnitude here. And this is then the ambient reflected light. It's also kind of greenish here with the largest coefficients at green. Yeah, and finally we can turn it on. So everything is enabled. All the lights are on. So let's take a look. So now I let it run. I'm using Python 3 here. Python 3. Yes, so this works. So here you can see it. This is our solid cube. And we have 2 lights. So one comes from more or less above here, and one comes somewhere from the right. And we can see this surface is illuminated from the ambient light, and this comes directly from the light sources. And you can also see we have slightly different colors because I gave them different light colors. Yeah, so that works nicely. And we can also now try to turn off light number 1 I mean, and try it again. So now we only have light number 0. We can see here that it comes from above and is more reddish. And here the other surfaces are not well lit, so they only have light from its ambient, from the ambient light. So we can also try the other light. So now we activate number 1 only. So this is now light number 1. Yeah, you can see here light number 1 has a different color. It's more greenish and it comes more from the right hand side, so it's up and towards the right, because now also this surface is more illuminated and this is still in the dark, but it's brighter than before. So now here we have a stronger ambient part, so that also works nicely. So let me activate both lights now again and now try a different object, like our teapot. The teapot is nice. So yeah, so here you can now see our teapot. You can actually now easily see our flat shading, right? Because you can easily recognize all the different polygons on this teapot. And you can also see the two lights. So the reddish one from above and the greenish one from above towards the right. So here, depending on where those surfaces point to, you have different light colors because of the different positions of the light sources. So that worked nicely. And we can also change the shading. So let me try smooth here. Smooth. Let's see if that works. Yes. So here you can see this is just a change of the shading from flat to smooth. And now basically all the structure from the polygons is gone. Right? All you see is round surfaces, even though this is a really simple model. Right? It doesn't really do much except for the interpolation. But you also see there is no shininess, right? Because we have this smooth interpolation. So I guess I should also keep the other one in. GL shade model GL flat. So going back, let's check it. Yeah. So here you can see indeed. Now we can nicely see all the polygons of our teapot, and also still the different light colors from our light sources. Okay, so let's go back to our simple cube. Yeah, so that shows that it works, right? So we saw the different lights can be switched off by commenting out the light switch GL enable, and by changing the color components, the different light colors of the sources and the color of the specular reflected light and ambient light can be changed separately, as we saw in the different numbers. The degree of reflection can be changed by GL shininess. This can be observed especially well with light number 0. Yeah, that might also be interesting. The solid cube can be replaced by solid sphere and or solid teapot by commenting out the desired to observe these effects on them. So let's try the shininess. So let's go to the sphere. With the sphere you can actually observe it best. So I didn't do the sphere yet. So here's the sphere, right? Again, flat shading, which is not so great. And let's see. So it's best seen with light number 0. So maybe I can turn off light number 1 and change the shininess. Where do we have the shininess? Here's the shininess. So now we have a lot of shininess. Let's go down to 1. Yeah, so this looks interesting, right? So basically we just have this light from above, and that's it. Let's try it with smooth shading. So we don't have much ambient light, and that's why we don't see much of the rest of the sphere. So here now for yeah, this looks also interesting. So we still see those polygons, even though we now turned on the smooth shading. So now let's try more shininess. Here, let's go back to 127. Let's see what it does. Yeah, so this looks actually a lot better, right? So here we have this shiny reflection from the light. It looks sort of natural, except that we still have those visible edges from the polygons, but it's not too bad. And we can also try it from the Teapot, the same. Let's see what the Teapot is doing with this shininess. Yeah, it's not looking too bad. So here you have more polygons, and we have this smooth shading, and you can see here nice highlights from the light above. So it's actually a nice picture. Yeah. Okay, so let me turn this back on and go back to a solid cube here. So you can see you can do your own experiments in this way and see how the result changes when you change those coefficients. Yeah, back to the slides. So often we don't have those predefined objects, but we have our own object consisting of polygons, and for that we need to attach normals for OpenGL. So we have a polygon and a texture, and we want to illuminate it. So for a polygon we need to specify the normal vector so that OpenGL can determine which side of a closed body is facing outwards towards the camera or in the other direction. So a polygon is assumed to be part of a closed body. So in my example it's not really the case. I'm just using a single polygon for simplicity. So the normal vector is specified with this GL normal 3F. So F for float and 3 for 3D. So for instance, here we define a polygon with its edges and vertices, and here we define the normal for it, for this polygon, right? And here we give it the coordinates, 3D coordinates, X, Y, and Z. And an example here is this polygon normal light texture. So let me open it, copy, gedit, and here we can see it. So here we have the display function with the virtual camera, and here we have the polygon and texture coordinates. So here we have our polygon, and this is the normal. Here I'm defining the normal for this polygon. You can see X, Y, Z, so this is actually just pointing towards the camera, directly towards the camera. And here I'm defining my polygon consisting of 4 vertices, which you can see here. So this is the vertex, and I'm connecting the texture coordinates to each vertex, as we already saw, right? So for each vertex I also have texture coordinates so that I can map my texture onto it. So now we have texture plus we have this normal, and that means we can now illuminate this polygon including this texture. So this is done then as part of the main loop where we define our window again. Here I'm reading in the TU Ilmenau logo as image, which you want to map. Here I flip it as usual. And here you can see I'm defining smooth shading as before. And here I'm having specular component, shininess, ambient light, diffuse light source, and I again have two light sources, light 1 and light 0 as before. Right, here you can see I activated light number 1, so let me also activate light number 0. Yeah, and here I'm doing the mapping of the texture, here the GL nearest filtering, and that's it. So let's try it. Both lights are on. Python 3. Yeah, so here you can see it. This is now our polygon. The surface normal pointing towards the camera, and we will see this TU Ilmenau logo. And we can also now test what happens if we let the normal point into the opposite direction, away from the camera. So here the Z coordinate now points away from the camera. So let's try. So this would be then on the other side of an object, and you can see there's basically nothing left, because this is supposed to be an invisible polygon, right? So that's why we need to go back to minus. So now we can also see what happens if we turn off one of the lights, say light number 0. We just keep light number 1. Yeah, so you can see now it's less light, right? And it's also slightly different light color here, because those lights have slightly different light colors. Yeah, so this shows it works, right? So in this way we can create more complicated 3D models using those polygons and those textures, and let them shine in our 3D scenery. Right, so yeah, so the sign of the normal vector determines whether the texture on the polygon is illuminated or not. So only if it points towards the camera it's visible, otherwise it's not visible. Okay, so that should be it for today. Thank you for your attention, and then see you in the next video.